Okay, in this lesson, we talk about double integrals over general domains. So double integrals over general domains or regions. So let's see how this is related to what we have done before and how it is different from the type of double integrals that we did in the previous lesson. So just as a reminder, in the previous lesson, the regions that we considered were rectangular regions. So as a note, the regions of the previous lesson were rectangular regions. So for like in general, when we had a rectangular region, suppose I differentiate with respect to y first and with respect to x, and y runs from C to D, x runs from A to B, and the function I call that f of x and y. So the region that we are integrating over, so x runs from A to B. So I'm not talking about the surface of the function. I'm just talking about the region that we are integrating over. So x runs from A to B and y runs from C to D. And these are given constants. So assume that in the xy plane, this is A, this is B, and this is C, and this is D. So the reason that we call it rectangular, as you know, it is because the region that we are integrating over is this region right here, this rectangle. The points in this rectangle satisfy these inequalities. X, every point, no matter where the point that we get on this rectangle, x is between A and B, and y is between C and D. And we were integrating over such regions. But sometimes the regions that we have are not exactly rectangular, but similar integration with the explanation that I will provide will work. So a more general region could look like this. And in fact, that's the subject of our topic of our lesson today. So the more general region is that we have two functions in terms of x or y equals these two. Y equals two functions gives us two curves. Suppose the lower function is y equals g of x, and the upper function is y equals h of x. And x runs from A to B. Now, the region that we have now will be this region. And we are integrating over this region. Now, the points in this region are satisfying these inequalities. The y coordinate is between g of x and h of x. And x itself is between two constants from A to B. As you will see in some examples, g of x is just equal to 0, meaning that y equals 0, and it is the x-axis. But I wanted to make a general statement for this kind of regions. So the lower limit or the lower boundary of the region is g of x. The upper boundary of the region is h of x. So the function that we have again is f of x and y. And I integrate over this region. In this setting, that y is between two functions of x and x between two constants. Make sure that the interior integral is dy, the exterior is dx. So y runs from gx to hx. And x, the exterior integral, runs from a to b. And at the end, when we do this integral, we should come up with a number. As you know, that number for the case that the surface of the function is above xy plane gives us the volume of the solid, which is trapped from above by the function fxy and from below by the region which is in the xy plane. So that's how we set up the double integral. But before doing that, let's for now focus on the region and do a couple of examples that we determine the region. So for now, instead of computing the double integral, we just focus on the region. But of course, after these examples, we'll start computing double integrals over general regions. So suppose I want to sketch the region for this double integral. The function is not important here. Of course, for the computation later, that's very important. But now I just focus on the region. That's why I show the function by f of x and y. Y runs from x squared to the constant 25, and x runs from -5 to +5. I just focus on the region. The region is determined by the limit of the integral, or by the limits of these two integrals. So this tells me that y is between these two functions, x squared and constant 25, while x is between these two constants from -5 to 5. So how can I draw this region? First of all, let me draw these two functions, y equals x squared and y equals 25. As you know, y equals x squared is a parabola. So this is y equals x squared. Y equals 25. Suppose 25 is here. Obviously, I'm using different scales on the x and y axis. So suppose 25 is here and y equals 25 is this horizontal line. So this line, the horizontal line is y equals 25. And x runs from -5 to 5. Obviously, when y is 25, the corresponding x on the parabola is, or in fact, are 5 and -5. Because it is y equals x squared when y is 25, x is either 5 or -5. So now what's the region? While x runs from -5 to 5, y is between x squared and 25. More than x squared, less than 25. So it is going to be this region, this shaded region. So this is the region that we are having in this example. The purpose of this example was just to sketch the region that we are integrating over, but we haven't integrated yet. In fact, f of x and y was not even given here. Another example, as usual, please try to do this on your own. And the next example also focuses on finding the region. So I sketch the region. For this double integral, the integral x runs from 0 to 2, y runs from x cubed to 4x for some function f of x and y, and dy dx. So here the region that I have for that y is between these two functions, x cubed from below and 4x on the top. And x itself is between 0 and 2. As you know from more elementary courses, that y equals x cubed, the cubic function looks like something like this. So this is y equals x cubed. And y equals 4x. Let me show it in a different color. Is a line passing through the origin. So this is the line y equals 4x. And x runs from 0 to 2. If you intersect these two functions, 4x and x cubed, by solving an easy equation, you will get that x here is going to be 2. Now you have a clear idea where the region is. The region is the y coordinates is between x cubed and 4x, and x runs from 0 to 2. So this is the region that we are integrating over. So while x runs from 0 to 2, the y coordinate is between these two functions, more than x cubed, less than 4x. So this is the region that we are talking about. Okay, now we get to the calculation of double integrals over such domains. So of course, in these examples that I want to calculate the function and also the region should be given. So calculations of double integrals over general domains. In this example, x runs from 0 to 1 and y runs from 0 to x. And the function is 4xy and dy dx. So I want to find what value this double integral is. The calculation is very similar to what we did for the rectangular case, but the main difference is here y runs from 0 to x. It's not from a constant to a constant. Like x is involved in the integral related to y. So this is the interior integral. I focus on that. So for now, I leave the exterior integral as it is. For the interior integral, 4x is a constant, can be pulled out of the interior integral. And so what I have is the integral from 0 to x as y dy. So integral from 0 to 1 for x and this dx at the end. Now let's find this. Antiderivative of y with respect to y is y squared over 2. And this should be evaluated at the endpoints of the integral. So I will have from 0 to 1 4x and dx at the end. So this integral evaluated at x is x squared over 2. And at 0, it is 0. So that's just x squared over 2. So when I evaluate y squared over 2 at x, it means that replace y by x, which gives me x squared over 2, minus the evaluation at 0, which is 0 squared over 2 is 0. Okay, here 4 over 2 is 2, and that 2 can be pulled out of the integral. X times x squared is x cubed. The rest is just a calculus 1 type integral, so 2 times antiderivative of x cubed is x to the 4 over 4. It should be evaluated at 0 and 1, so 2 times the evaluation of this function at 1, which is 1/4, at 0, which is 0, and 2 times 1/4 is 1/2. So the value of this integral is just 1/2. Let's go to the next example. Again, I will strongly recommend that you do it on your own before watching the solution. So the next example is the integral from 0 to 1 x runs from 0 to 1 and y runs from x to 2. The given function is 6xy, then dy dx. Again, for the interior integral, 6x is a constant, can be pulled out of the interior integral. So 6x here, I have the integral from x to 2 of y dy, and then dx. So this is the integral from 0 to 1, 6x. Antiderivative of y is y squared over 2, and it should be evaluated at these limits. Y squared over 2 at 2 is 2 squared over 2, which is 2. And at x, it is x squared over 2. Distribute 6x over these parentheses. So what I get is 12x minus 3x squared, 3x cubed. 6 over 2 is 3, and x times x squared is x cubed. Now, antiderivative of 12x is 6x squared. Antiderivative of 3x cubed is 3/4 x to the 4. And I need to evaluate these at the limits of the integral at 1 minus at 0. At 0, both of these two terms are going to be 0. At 1, when x is 1, this is 6, and the other one is 3/4. I just need to simplify this. 6 minus 3/4 is 21 over 4. And that's the final answer. Again, try the next example on your own. And the next example is the double integral. X runs from 0 to 4, and y runs from x squared to 5x. The function that we have is x cubed. Sometimes the f of x and y can be only in terms of one of the two variables. So it's x cubed, and I have dy dx. So for the interior integral, x cubed is a constant with respect to y, so it can be pulled out here. So the integral from 0 to 4, x cubed, and the integral with respect to y of, in fact, 1 is remaining, or just dy. And the exterior integral is dx. Antiderivative of 1 with respect to y is y. With respect to y is going to be y. So the antiderivative of 1 is y. It should be evaluated at these two functions, which gives me y evaluated at 5x is just 5x, at x squared is just x squared. I distribute x cubed over these parentheses, so the integral from 0 to 4. 5x to the 4 minus x to the 5. Antiderivative of 5x to the 4 is x to the 5. Antiderivative of x to the 5 is x to the 6 over 6. And I need to evaluate at the limits of the exterior integral. So I evaluate this at 4 minus this evaluation at 0. At 0, it's 0 at 4. 4 to the 5 minus 4 to the 6 over 6. It just remains to do this calculation and come up with the final answer. If you do it correctly, you should get 1024 over 3. So that's the final answer for this example. The next example, again, please try this on your own before looking at the solution. The x runs from minus pi over 2 to 0, and y runs from sine x to cosine x. And I have dy dx. I don't see any function there, so by default, that function is just 1. So when we don't see the function there, it is 1. Okay, so first let's do the interior integral. Antiderivative of 1 is y. And that y should be evaluated at these limits values, which are functions of x, and we should do the subtraction. So the integral from minus pi over 2 to 0. Evaluation of y at cosine of x is just cosine of x. At the sine of x, just replace y by sine x. Now this becomes a calculus 1 type question. Antiderivative of cosine is sine minus antiderivative of sine is negative cosine. And it should be evaluated at these limits, and we should do the subtraction. First of all, this is going to be sine x plus cosine x. Double minus makes that plus cosine x. Okay, the evaluation of this function at 0, sine of 0 plus cosine of 0, minus the evaluation of this function at minus pi over 2, sine of minus pi over 2 plus cosine of minus pi over 2. Sine of 0 is 0. Cosine of 0 is 1. Sine of minus pi over 2 is negative 1. And cosine of minus pi over 2 is 0. So the final answer, 1 minus negative 1, which is 1 plus 1, and equals 2. So the value of this integral equals 2.